Welcome to the NewSpace India podcast, a bi-weekly talk show that exclusively captures insightful conversations with people contributing to advancement of space activities in India. The NewSpace India podcast is pleased to announce our association with Dassault Systems, a global leader in providing business and people with collaborative virtual environments to imagine sustainable innovations. Dassault Systems solutions support startups, small and medium-sized enterprises, and original equipment manufacturers in developing disruptive solutions for space launches and satellite propulsion. Recently, a supply chain digitization study with Dassault Systems was conducted to provide a foundational understanding of the supplier landscape in the Indian space ecosystem. Please use the link in the description to download the public white paper of the results of this study, which will also give you a perspective on how ready Indian suppliers are to enter the global space market. Hi, everyone. This is the NewSpace India podcast. And today we have Mr. Surendra Vaidya, who is the Executive Vice President and the Business Head for Godrej Aerospace. Welcome to the show, sir.
Thank you so much.
So Godrej has been a very big name, of course, associated with the Indian space program, and your contributions have been there for many, many decades. Before we get to Godrej itself, I want to learn about what got you into Godrej and what got you into the aerospace division and how Godrej started the aerospace division and started collaborating with ISRO.
Okay, so thank you, Dr. Narayan. Let me start with myself. I think that will give some background of how I got into this aerospace. I'm a 1983 graduate from IIT Mumbai, IIT Bombay, with metallurgy as my subject and specialization in welding. And that actually brought me into the fabrication area as I decided that use this welding knowledge, what I got in the last 1 year of the graduation, to the little practical experience of what I will be able to correlate with. And that is how I joined Larsen & Toubro and got into various special fabrication areas. I mean, that's the time when 83 Larsen & Toubro was looking for setting up new facilities at Hazira. And they wanted to start with the offshore platforms. It was a very large yard what they took it. And for the first time, a new code, a new set of materials, new welding standards, new fabrication standards were required to be studied, because Larsen & Toubro was earlier to that was into the pressure vessels. And that gave me exposure to various international codes, because in India, by that time, the codes were not established for the offshore platforms. And this exposure to the international codes and the specifications, plus I think the different materials, because most of our pressure vessels, by that time, we had not a technology to set up these facilities near seashore. Most of our refineries, petrochemical industries, they were deep inside earth, and most of them, they were using sweet water. But now the technology was changing, and offshore platforms, as you know, they have to be on the sea itself, on the ocean itself. And that's why these new materials were required to be studied. However, the working conditions that time at Hazira, Surat, and the Surat city itself was not that good in 83, 85. So, started looking back once again, standard of living will be really good. And you must now look into it in a little different fashion also. I would say among the batch of 36 whom we passed out in 83 in the metallurgy, we were the only 4 who stayed back in India. Otherwise, all other 32 were moved to US for doing higher studies or getting into, that time I think the software was at a peak. So we started comparing ourselves. Had we made a mistake of staying back in Mumbai, in India, and then that to going into a remote place like Hazira and Surat, which is not a very good city to live. Of course, now situation had changed a lot. And then we started looking back for opportunities, and Godrej that time was entering into the pressure vessels, and they wanted some good engineers to support them in welding and welding technology. And that is how I got into the welding. of Godrej pressure vessels. That time we used to call that division as a Godrej Process Equipment Division. Now, this is the same time in the 80s, Government of India, Department of Space, Indian Space Research Organization had concluded most of their R&D, and they were looking for private industries to come forward and participate in their manufacturing, so that the R&D work can be done by the scientists rather than getting involved into keeping themselves into busy in manufacturing. Now, obvious choice was Larsen Toubro, Walchand Nagar Industries, because they were experts in engineering at that time. But at Godrej, we used to have very specialized knowledge in machining of very critical parts and components for our own tool room. It was not that we were doing it for anyone else. We were doing it for our own usage. But Mr. Nauroji Godrej, father of our current chairman, who was the chairman then, he was very fond of machines, and he used to really move across all over the world, and whatever machines he will feel that these are the best in class, he will buy and position them in tool room. So that our tools, and that is how all our consumer products, we started segregating ourselves from the rest of the consumer products, whether it is locks or cupboards or refrigerators or any other consumer product. You will see that the kind of finish we were getting, the kind of accuracies we were getting, kind of reliability which was there in our product, that was quite different even in the 80s when technology of manufacturing was not that good as what we are having it today. So as a result, what happened, we started getting into very large number of complex capability machining as well as fabrication machineries into Godrej and Boys. Now, ISRO identified that. They approached Mr. Noel Godrej and told him that since you have all this good machinery and understanding of what is precision and how to really make it on a mass scale, we would be very happy in case Godrej gets participated into the programs of national importance, and especially the space program, which is for peace. Not like the defense where you may have a lot of other issues which are cropping up. And then he was taken across most of the facilities of Indian Space Department. And he was thrilled that the kind of work which was done in the initial old days by very limited resources. I mean, India still has very limited resources as far as the space or defense is concerned. And those limited resources, the kind of achievements our scientist has done. So he immediately on the spot committed to the chairman, Professor U.R. Rao, and said that yes, the only condition what he put is that we will require some hand-holding, because we are not really into the aerospace or into a high technology engineering products. We are into consumer products, and we will require your hand-holding. And Professor Rao was very gracious to, he says, yes, I will ensure that at least few of my scientists who are good in manufacturing, they will be positioned at your place till the time you feel confident that now you can run it on your own. But when they came here and they found that in the tool room, we had no metallurgist, no understanding of different materials. And in the space programs, we use exotic alloys, whether it is aluminum or titanium or in nickel-based alloys, or even the various grades of steel. But they exhibit very high strength, because in aerospace, weight is the single most criteria for design. It has to be as light as possible. And it should be having very high corrosion. It should have very high temperature withstanding properties. It should be able to give a lot of toughness. So these are possible only is using these exotic alloys. And then when we started using this, ISRO started feeling that that something is lagging. I mean, even though we started attempting machining, we started attempting some specialized surface treatments, heat treatments, and then tool room started hunting for some support from the metallurgy. And since we were part of the same group, immediately that information was given to the process equipment division, and then I was identified to go and start helping tool room in making them understand these materials. What are their characteristics? What is their behavior? And that helped me because I had educational background, which is from the metallurgy. The first 4 years I got into Lassen Tubro, where I got into this different materials, how to study them, how to characterize them. Because another difficulty in aerospace is, even though we use very vast materials, but nobody will share the actual physical characteristics. You will come to know only few characteristics, but not all of them. You need to characterize all of them yourself and learn with your own experience. No textbooks gives the kind of properties what are required beyond clearing the examination. I mean, you require a lot of other knowledge when you are actually going to start manufacturing the products and articles out of it. And that is how we started a joint venture between the process equipment division and the tool room division to look into all the parts of ISRO. And then ISRO got a confidence and we started developing parts in titanium and other exotic alloys. Their scientists were available. We had our own experts in various manufacturing processes. I was contributing from the metallurgical side. And we started developing those parts. In the first year itself, we made about 25,000-30,000 worth of parts. I mean, in 85, 87, this 25,000 parts was also quite a large in numbers. It was not only one or two parts as we will get it today. We produced almost 200 parts, very critical parts. And all these parts, when they took it back to their facilities in Trivandrum and Bangalore, they assembled and found that the kind of tolerances, the surface finish, the accuracies we gave were very good. And ISRO was very happy. At the same time, we were very happy that we didn't reject any of the material. We could use whatever was given task to us, we could make it. And from a very traditional consumer product to a high technology product, the transition of at least these 200 parts was very. And then ISRO started giving us more and more opportunities. Started building parts of SLV and ASLV. At time, these were the two launch vehicles, the satellite vehicle and augmented satellite launch vehicles, ASLV. And very complex machining processes were involved. In addition to that, when they visited our process equipment division, where we had lots of welding technologies, they offered us a lot of sheet metal and welded parts. And then process equipment got into this business of manufacturing the fabricated welded parts of SLV and ASLV. And in 1989, ISRO had a very big opportunity which came to India. Before that, if I take you back in 80s, between Government of India and Government of France, there was an agreement and a jointly developed, about 40 scientists from ISRO were deputed to France, and French scientists who were already deep into the space. They started developing a liquid engine called Viking engine. When it was moved to India, we started calling that as a Vikas engine. And that was planned for by us into the second stage of PSLV. And whereas in European Space Agency, they planned this Viking engine in many of their missions, like Ariane and other missions, what they are using it over there. Now, of course, they have phased out these Viking engines. Vikas engines are still being used, and we have produced now more than 150 Vikas engines. But that engine was required to be manufactured in full. That means all more than 1,000 parts of those engines are required to be made from the various raw materials like aluminum and nickel-based alloys. And they had a very special alloy which was used in the entire thrust chamber. It was a cobalt-based alloy. And this is a very, very tough material to weld and work upon. But once again, with our experience by that time into the space and into manufacturing various pressure vessels for oil and refinery, we could grasp that very well. And we won that contract in competition with the other competitors where I worked earlier. And the entire Vikas engine was awarded to us in 1989. And there was a lot of restrictions because the government of India and the DRDO had their own missile program and fighter jet programs by that time. And like ISRO, they were also contemplating to identify private industries and use their skills. So there was an international ban on India to import the critical machines which were required to manufacture those Viking engines or Vikas engines. So we decided, with our background of Godrej into the machine tools, we decided to make all those critical machines in-house. And that was our first task, to make all the critical machines, the SPMs, the special purpose machines. And from there, then move to developing various technologies. Once the infrastructure, the resources are available, we started developing into the actual parts. But before that, there was a technology development. So it took us about 5 years, and in 1st January 1994, we handed over our first completely Indian-built Viking engine or Vikas engine, and that underwent successfully all the ground tests. There are lots of ground tests which are required to be completed before you go on to the flight-worthy certification. And those certifications, when obtained, there was huge applaud between the ISRO, DRDO, and all the aerospace community in India. And then Godrej was identified as one of the major partners to be with ISRO and DRDO. And then we started getting the cryogenic engines and so many other engines what ISRO were developing, as well as from the defense side. And then Agni, Prithvi, Trishul, Akash, Nag, all those IGMT programs and various other programs, we started getting involved into it. So that's how the entire thing started. I mean, it was not really the intent of Godrej, but we were identified by the customers to get into it. And from the day we got into it, we never looked back, and we started understanding, learning all those international code standards, ISRO standards and specifications into space programs, various materials, various manufacturing technologies, heat treatment, surface treatment, specialized non-destructive tests which are required to be conducted, all the simulations, the accelerated test, because if you are making a part of a satellite, it has to have, in those days, we used to qualify them for 7 years and 10 years. We have started qualifying those parts for 12 years and 15 years. So the technology is improving, the perfection in design, perfection in manufacturing has improved. And once we saw that now things are well established, we started getting into almost every program the ISRO and DRDO will come out. Then we had more than 400 to 500 different subsystems. Of course, till 2000 and around up to 2006, the numbers used to be very, very limited. I mean, if we make one engine in 3 years or 4 years, ISRO used to be happy initially. Now the scale has changed drastically, and now they're expecting us to produce about 20-25 engines every year. So from 1 in 3 years or 1 in 4 years to 25 engines in a year, that's a big change in volume. And as now the private industries and the privatization of space is going to take place, the government has already announced the policies, and the 2 new companies are getting set. The rules and regulations are going to be out. I think the next parliament, they are going to discuss about the space law. And if that gets into commission, I think this numbers, what I just narrated, will also be looking very small. And what we are talking in a year now today, maybe it will be required every quarter or every month in the coming days. So I think I took a little longer time to explain you the answer for your first question, but I will stop here. Let us continue with what you want to know more. Otherwise, I can keep on talking like this for next 2 days. We have done so much of work. India has a huge history in development, and Godrej has been participating it in the last more than 30 years. And I was there in every aspect of right from the first stone when we laid out.
Right. I mean, it's a fascinating introduction as such. So I appreciate that you took some time explaining all of this. I want to talk to you about this initial collaboration or initial identification that ISRO made with Godrej, and the initial days when you talked about how UR Rao, was involved in handling, this collaboration and then placing metallurgical experts from ISRO at your facilities. So can you talk a little bit about what was the early days of collaboration, how it evolved? Was it also more than manpower and more than training of your own engineers, maybe with space-based processes or reliability or quality standards? Was there also any capital support or equipment support or any other nature of support? And the nature of how risk was handled, because you're dealing with very high risk elements here, how the whole de-risking process or the risk and reliability was handled.
Yeah, so I will put your question into 3 or 4 segments. I mean, that way it will be very easier for me to explain it to you. As I talked to you earlier, the first for a company like Godrej and Boys by that time, which was into the consumer product, was to really have a transition from a very high volume production, what we are doing it, into a low technology to high technology. And the production is more of a product oriented production rather than the process oriented production, because you need to develop those parts. And like we were making some 400 refrigerators in a shift, so 400 refrigerators in 8 hours was something what I remember. And then we were making 1200 typewriters in 8 hours, and then some 600 cupboards in 8 hours. So that kind of volumes we were handling. And all our I mean the culture in the entire organization, right from departments to individual manufacturing, sales, to the quality standards, and to the procurement. I mean, every aspect of running a business was towards making this in larger numbers, in larger scale. And from there, when you go and start talking that I'm going to produce only one part a day, I mean, was very difficult for the core team. I mean, I was part of that core team to convince the other manufacturing people, because it was not possible for us to justify having our own machines with such a low volume. And the kind of revenue I was just talking, I mean, 20,000, 30,000 was a revenue in a year. So that is what we were getting. ISRO was supplying raw materials because it was very difficult for us to procure raw materials in such smaller quantities. So government used to buy material in bulk, and with government to govern from Russia, from France. And these are very classified, specialized materials. So nobody in the private sector will be able to even have access towards this material from the international market. So the materials were bought by the government, and they used to give material to us. So our part was only conversion. And that is where the turnover used to be very, very small. The second aspect, what you asked, is how they were really financially helping, because in such a small numbers, how do we justify investments? Whatever investments we are doing, or whatever tools, jigs, fixtures are required. For a manufacturing in aerospace, it is not only the machinery which is important and critical, but for every part, if you want to achieve in those close tolerances and repeatably, I think there is a lot of emphasis is given, and even today also it is true, is onto development of tool, jigs, fixtures, gauges, templates, because these are the tools which can give confidence to the operators and supervisors on the shop floor and the managers on the shop floor, that what part I'm going to make is going to really come out good. And the materials are very expensive. If you lose even in a lot of 25 one part, means about 4% or 5% rejection, is very, very expensive, because all these materials, even today, because we are heavily import dependent, and they are very specially produced with a lot of standards on cleanliness and on their that means we don't use any material which is melted out of the scrap. These are all melted out of genuine ore and from the prime materials. So they are very expensive. For example, a typical stainless steel, when we buy for utensils at home, we buy it at about 200 rupees a kg. But the same stainless steel, grade wise, it may be same 304, 316. But when you buy it for aerospace, you buy it at about 600 to 800 rupees a kg. So this is only in stainless steel. But when it comes to titanium, it goes to 50,000, 60,000, 1 lakh rupees a kg or something like that. And that means you cannot afford to waste. You cannot afford to reject any material. You have to be 100% sure. So that was the second training what ISRO gave us, how to really bring in reliability into the processes what you will choose, so that It's not the first time, but every time your part has to be good. You cannot simply afford to reject any part. There are two reasons. One is I explained to you about the cost of the material. Secondly, the import of this material, even though between government to government was easy, but it used to take a very long time because it has to go through lots of procedures before it is being cleared by government of India, and then when it goes to the USSR that time, or the government of Russia, or the Federation of Russian, and when it goes to the France, there also once again the same way the government approvals are required before the industry will supply it to you. So if you lose a material, you have to wait for next 6 months to get back that material from the sources. So how to bring that reliability? And when you bring that reliability, you need to understand the quality requirements very well. So what was talked to us, or what was taught to us, the tolerance stacking. You just don't get the tolerances in the last process of your machine. You have to start it right from the beginning. Really source the material, what kind of allowance you will keep it when you source a material, how you start machining it, at what stage you will do some kind of a stress living on that material so that the stresses will not show up as you start going into the next processes. And then how to really give the minimum fricturing forces, and then how to use gauges so you don't have to remove your job from the machine before it is being taken up for the final inspection. And the important part is that all parts should be inspected in free condition. They should not be under any constraint. When the parts are in free condition inspected and you are meeting the tolerance, then only you are sure that when you are going to assemble those parts, there will not be any internal stress. And all this was required because if you have to make any part which is going to be
It's 4:00.
used on to the ground, you have a very liberal tolerances as far as your safety margins are concerned. That means if you want by design calculation of 1 meter thickness for your table or chair, or for your any other equipment what you are going to do it, if you take instead of 1 millimeter 3 millimeters, only your weight is going to increase, but there will not be any penalty on that. But because you are going to use 3 millimeters, then your manufacturing processes, you create a lot of tolerance on it. They can be more forgiving. A small defect can be accepted because you already padded up your thickness by 3 times. So it can accommodate any defects in manufacturing. But in space, because weight is a constraint against 1 millimeter thickness, with great difficulty, we convince designers that we require something for manufacturing also to go wrong, or for the calibrations of the machines to go wrong, or between two machines and two equipments, there cannot be exact similarity up to the last micron. So they give about 20% or 30%. That means against a 3 millimeter watt, easily you will get it for equipment which is used on ground. When you use it in space, you get 1.1 or 1.3 millimeter thickness against 1 millimeter. That means now you have to be very, very vigilant when you are going to do on its manufacturing. When you are going to bend it, the thickness should not reduce. When you are going to machine it, you should not reduce any machining. And the last important portion what ISRO brought to us is that we are not only going to look into the functional requirements, we are also going to find out, after achieving the functional requirements, is there any material which is excess? Can I have some weight reduction pockets or weight reduction areas where I will scoop out the material to reduce the weight of that particular part, which is never done or never attempted in any of the equipments which are used at ground. Even for sea also, all these days, now only the optimization has started for ships and other seaborne vehicles which are being used there. But for aerospace, it is absolutely must to reduce on the weight. So first, to use very high strength, low weight materials. In addition to that, by design, you find out from where the material can be reduced. And all this is going to put pressure on the manufacturing teams. Because with all those constraints, you are now going to manufacture and achieve those critical tolerances. So that was the second training which we got it, that what are all the service conditions. Let me explain you about the service condition. I mean, the photograph behind you, it's in space. Now, whatever area which is facing sun is going to have something like 150 to 200 degrees plus centigrade. That's the temperature which you'll be seeing by that. Because we don't have in the space the ozone layer and the radiations are direct. So the heat which gets accumulated on the surface, which is facing the radiation, goes up to 150 to 200 degrees centigrade. But the one which is in the shadow, exactly at the backside of this, where there is no sun ray which is directly going and hitting onto it, is going to be exactly opposite. It will be at minus 150 to 200 degrees centigrade. So that means on the same component, you are going to have one side which is being seen at positive temperature and the other one is at negative temperature. And the temperature difference between the two ends is going to be something like 200 to 400 degrees Celsius. And that is where the designers have to use very specialized materials which has very low coefficient of expansion and which should have a very good temperature and physical properties against the temperature. And when we are going to use parts into the rockets, like the liquid engines what we produce, and why these specialized materials are required to be used, is where the actual burning is going to take place. That is where the temperatures are going to be more than 3000 degrees centigrade. So the material has to withstand that kind of a temperature on the skin, whereas on the other side you can give a cooling, or when it is in the space, other side is going to be at minus 200 degrees centigrade. But such thermal shocks, what are going to come? We don't want any smallest deviation also in the part, which can create a problem to absorb such kind of a thermal shocks, the vibrations. A typical automobile industry, when they design their car against our normal 1g gravity, when we walk, when we sit into a car, we go up to 4 or 5, and they design it to 8 to 10 times the gravity, so that the car will be still stable even if we accelerate it at very high speeds or at very high accelerations. To achieve from 0 to 6, we typically see the advertisement in the automobile sector that we achieve 0 to 60 kilometers per hour in just less than 15 seconds. So that is actually going up to 4 to 6 accelerations or 4 to 6 gravitational force. But in space, we are talking about supersonic speeds, and that too also in a very short span. And that is where we need to go from 6 to 8 gravitational force to 32 times the gravitational force. And that requires, once again, a lot of reverse calculations and existing tolerances to be reviewed, that in extreme conditions of all these shocks, vibrations, bumps, climatic conditions, whatever may be the condition, the material should be good enough, the component should be rigid enough to sustain. So that was the second thing. The third aspect what ISRO taught us is the success. How do we measure the success? If we have a successful launch and we have a successful satellite, any other vehicle, you can assemble, test it, once again, reopen it and make for yourself that, yes, I made provisions, assumptions, whereas it is not showing like that. Here we are not going to get any part back on Earth for us to study, whether it is a success or a failure. Even if the mission is a failure, it is going to go and make a big bump onto the Earth, or if it is going into the water, still it is undergoing a huge shock. So even if you are able to recover back this particular portion, you are going to see it in a damaged condition. So you really don't know what exactly happened during you fired the engine or when you operated a satellite. We don't have still the reusable vehicles. We don't have in India still the reusable satellites. So that is where getting back data is impossible. So the data only which is going to be available with you is the documents what you are going to generate as you are in process of manufacturing. And where we give a huge importance in documenting each and every aspect of our manufacturing. Who made it, on what day he made it, which machine he used it, what parameters were used, what the machine or the instrument which was used for measuring and calibrating it. And that record is going to later on give us the success story or the failure or a setback to the analysis, and we get to then improve upon and optimize on our various processes. So the documentation portion, which is neglected by most of other industries, was the first important part what was required to be taught to a quality engineer. That whatever you are going to inspect, whatever you are going to see it, you are going to document it. And in those 80s, we didn't had, like today we have IoTs and so many sensors and cameras and all that. It was not possible. Everything to be written down. We didn't have even the Excel. We didn't have a computer also to use. So everything has to be written down. And such huge pileup of documents are then required to be scrutinized before you can get a release note for shipping out that part from your operations to or your workshops to the ISRO. And then when the ISRO will start assembling and when the ISRO is ready for the launch vehicle, such humongous documents which are being created are required to be studied by someone physically. So you require a lot of your correctness when you are going to write down and correctness when you are going to read and tabulate and then compare and all that. So that was the second. The next point you asked about the infrastructure. I mean, when justification for this infrastructure was not there because the volumes were limited, I think ISRO came forward and they used to support industry in two ways. One is against an order, which used to be a very small value, but they used to give quite a good amount of advance so that you don't really put your own money and wait for 10 years and 12 years to have a recovery on that. So they will give you advance to make an investment. Secondly, they will also give money for making the project specific investments, like all these tools, jigs, fixtures, special purpose machines. The general machines which are used in any fabrication, that was supposed to be the responsibility of industry to be bought. The area, the infrastructure, that is specialized rooms of 1 lakh class, either cleanliness rooms or temperature controlled rooms, that was the requirement of industry to do it. So I will say it was like a 50-50% partnership. 50% will be invested by industry, 50% will be invested by ISRO. ISRO will invest into project specific investment, whereas the industry will invest into a general purpose machines and the infrastructure, which they can, if these attempts are not successful, can divert it into any other product. And ISRO was putting money from the project specific in their developments as a part of their R&D. So that's how this entire thing started getting developed. And it was a very good model. And once they will identify a particular industry for a particular project, then they used to really handle it. I mean, I have seen as many as 25, 30 engineers used to be coming from Trivandrum, Bangalore, Ahmedabad, and various places wherever they had the expertise in manufacturing and talking to our people, because speaking in local language was very important. The operators, workers were not very comfortable. Today, most of our workers can 100% understand Hindi, and most of them also have computer knowledge. English is also quite well understood. They may not be able to speak, but they can understand. But that was not the case in 80s when we started operating it. So they used to get there who were available at various locations and come here and speak at least in Hindi, if not Marathi, which is a local language here. But that's how they really built it. And then the last phase came up where we were ready with the infrastructure, we were ready with the quality understandings, we were ready with our initial qualifications, trainings, and station of our facilities. And then they started bringing in the product knowledge. I mean, we never got involved into manufacturing a part. We always got involved into manufacturing a part which is going to take a satellite and which is going to get us some kind of a benefit, either by remote sensing or by communication or by water data and other things. So like, it's not I'm cutting a stone, but I'm building a temple. So that kind of a culture they really brought in. And every worker every supervisor, every manager, every general manager, and whosoever wanted to attend, right from Chairman ISRO and the directors of various their laboratories, they used to come and explain us as to how the entire mechanism works and what is the criticality, why we are demanding so much of quality and why we are demanding so much of alertness and attendance in you. So I think all these 3-4 aspects what ISRO brought in, that really helped us to learn, assimilate all that what they were trying to tell us. And then in the next phase, we started putting our own efforts in. As to now, ISRO has built the bare minimum what is required into the space. Now, how do we really use our knowledge of mass manufacturing or optimization, productivity, productionization, cutting down on the cost, and then how to become really competitive, not only in India, but in the international market. And that, I think the combination of the ISRO's initial efforts and then the private industry's efforts of converting that into more efficient way of manufacturing and then giving them suggestions, improvements, that has really helped us to bring it to the current levels of our manufacturing.
And one of the things that I would like to now, touch upon is you explained very beautifully the whole process, the hand-holding, the initial collaboration, and you brought it to a level where people can now think about what is your own innovation, as you said, because it's one of the fascinating journeys where you see somebody who is doing high volume manufacturing to pull them towards low volume, because normally it's always the other way around that people want to think about, saying I'll go from low volume to high volume, and in your case you're going from high volume to then low volume, and learning a lot of the new things around reliability and new conditions of operational environment and so on. But after that, can you talk a little bit about how your own experiences after absorbing all the knowledge, and how your own innovations have come about in making this engine more reliable, or manufacturing it to a reasonably better standard, or whatever those innovations can be, based on your own internal processes and your own internal learning. So what is kind of your innovation on top of what the knowledge in the initial handholding that ISRO has given to you?
Yeah, so as I said, we brought in our expertise in the mass manufacturing. That means if I have to get this part again and again the same way, and that is what they were expecting, it is not only the first time right, but every time right. So I think the kind of tools, jigs, fixtures, what we improved and what we made it, and by making this, there are two advantages. One is that the manufacturing of the part becomes easy. But second important part is that when the volume started going up, and when we wanted to have more and more operators to get involved into it. So after having perfected our technology in tool, jigs, fixtures, then we started looking for how do we start into the automation. So the combination of good fixtures and automation will help us in de-skilling the requirements. And once you have a de-skilling, the multi-skilling becomes easier. And when the volumes are going to go up, the two CNC machines can give you exactly a repeatable parts. But two operators, even though they are skilled, experienced, trained, qualified, getting exact repetition between two of them sometimes becomes difficult. So the help of the tooling, the help of low-cost automation, that really helped us. And now, of course, we have all those various tools, sensors, and IoTs which can be deployed, so that even if two operators are going to do it differently, still be as close as like two CNC machines. So that was the first expertise. We started using it from the Godrej side into perfecting this aerospace technology. The second important part in any manufacturing is how to really reduce on the non-value added activities. When you do research, or you always made so that you don't really lose any part, and you still have a lot of freedom to alter it at a later date. But when you are in the serial production, assumptions what you started with. So we used our good DOE, the various design of experiments. So even though we were not getting into the product layouts, but we started optimizing the material movement to very great extent and reduce the material movement by laying up our process layout itself in a better way and making the handling of the components and very easily, so that there are no efforts while this, because all these parts are very thin and flimsy. It's only when your entire assembly is complete and ready, it gets some strength and the stability. So that was a second aspect we brought in. The third aspect is we started our own training center, because when it was a small team of about 20-25 engineers and operators, it used to be very easy to communicate and train. But then later on, when the business volume started growing up, the team members started growing up, and today we have about 500 of us. So how do we really communicate well, and how do we really train each other so that my output is somebody's input, and there should not be a difference between my output and his input requirements. So we started bridging those gaps between the two, and effective communication between the two team members of what is required by me. Like we always say that if I have to weld right, I have to set it right. But if I have to set it right, I have to cut right. So it is not only the welder who is responsible for his final weld joint, but it is the first operation when somebody is going to cut the two parts and somebody who is going to join it together. So how do we build that cascading effect of quality from one process to the previous process to its earlier process and to its earlier process? So like that, we put in a lot of efforts to educate each and every one as to your small mistake in cutting can create a havoc when we are at the final stage when we are going to weld it. So like this, we started using a lot of good manufacturing principles and the tools which are available by that time, like TPM, and then we have the Six Sigma, and then now the lean manufacturing, and then the quality function deployment, and statistical process controls. On a smaller volume, how to really do a good statistical process control was one of our challenge. So we changed that particular thing, and instead of measuring number of parts, we started measuring the parts made on a particular machine or parts made by a particular operator. A different part, it can be a different project for which he is making it, but as long as it is on the same machine, as long as it is by the same operator, whether are we going to get a consistency, and then can we have a statistical process control to really monitor and understand that the processes are under control. So rather than inspection, we started moving back into the basic processes and perfecting those basic processes, so that once you have a process under control, your quality is automatically going to be assured. You don't have to really inspect onto it. And this is the way we started using our expertise from what we learned from various other products. And lastly, instead of just using these particular technologies, the processes what we learned for space and defense, we started finding it out, can we have some kind of a spin-off into the commercial products? And if we can do that, then I think we'll be able to accelerate, because if we produce more parts with using the same process, maybe for different applications, but that process gets perfected, and the whole emphasis was on the process. So we had some critical processes like electropolishing, very, very difficult to monitor and control. So we found that such processes extensively can be deployed into man-made fiber, synthetic rubber, and then pulp and paper industries, where you have very, very sticky materials in which you use it. And this electropolishing technology helps you in getting you a non-adhesive surface. Similarly, the titanium, the inconels, what we use, the inconels are having very high usage in boilers. So we started putting our operators into manufacturing of boilers. The titanium is extensively used in desalination plants. So all these learnings from ISRO or from the space programs, we use very effectively. It's spin-off of those technologies. Welding of titanium, not very easy. But once you do it, manufacturing of the desalination plants becomes extremely easy. And titanium is the best material for doing desalination plants. And we have many examples in India where we have fabricated such desalination plants and more than 250 electropolished reactors for various industries, and then the other inconels for boilers and various furnaces. And that really helped us, that we are not then restricted only to making one or two parts, and the welders, the fabricators, the machinists, the inspectors, the NDT personnel, everybody had then a sizable volume to really work on, rather than working on a limited volume and then waiting for the next engine to really get released so that we can work on it and then remember everything. And if you don't practice, you tend to lose that skill. So if you practice, your skills are retained, but if you don't practice, your skills are likely to get lost. So I think this combination of the space and some of the consumer products, I would not call it consumer product, but a specialized product in the other industries where you can have some volumes and some continuity in work can be maintained. So that really helped us.
It's an excellent example that you talked about, the spin-offs, often very disregarded or not very well credited in many aspects, and not also very well documented in many aspects with respect to how other players are using this. So one aspect that is also again interesting is this scaling up of production that you talked about, from one every 4 or 5 years to 25 a year to possibly you said maybe 100 a year in the upcoming years. What is the preparedness that is needed, and the strategy that is needed to meet such volumes?
Yeah, so we have taken two major aspects. One is that we are now heavily automation is one of our mantras. I mean, we are trying to find out each and every process so minutely and so perfectly, so that the automation becomes easy, whether it is machining, whether it is assembly, whether it is welding, or even if we go for surface treatments and heat treatments. Everywhere we are looking for opportunity to automate. And then second important, I think we are started moving now from a process layout to a product layout. So these two major changes we are implementing in the last 2 years. We have implemented it very successfully, and some of the civil aviation work where the volumes have already been quite large. Of course, now the pandemic has brought down the civil aviation to just 20% of its the peak what we were running it in 2019 and the first quarter of 2020. But we have been very great success in implementing both of them. Value engineering is the third area which we are starting it now, to find out how to really optimize it. I mean, everything, should we start from a rod, or should we move over to a forging or a closed air forging? We move from metal to non-metal, or should we really deploy the current way of manufacturing or change it? So we are moving from conventional 3-axis machine, 5-axis to 9-axis to multiple axis machines now, so that once you load a part in form of a rod, you just keep on finishing the part from both ends, rather than having multiple setups and then realizing that part. So the technology is changing. Third important part is we are also exploring now the new technologies like 3D printing, and then isopropyl forming, and then
It's 4:30.
I mean, the impulse forming, and there are so many other ways of really getting you a shape. You don't have to really everything has to be machined off. So you can form it using a sheet metal, using the lightweighting concepts are being used. Many times we are using it, most of our components from a tube or a pipe, rather than making it out of a rod, and then saving weight, and then saving machining efforts also. So like that, the newer technologies which are coming up are also being brought in. Lastly, as I mentioned, we are also working on IoT. So in all our fixtures and all our machines and all our various test equipments, we have lots of small sensors which keep on capturing very critical data. For operator, it will be very difficult to do it when he is actually working. And the final thing is, I think, a tremendous impetus and focus which we have brought into the safety. Huge efforts have been taken up to improve on our safety. So every workplace or the work center has been ergonomically designed. We have identified all the possible incidences that particular work center can give rise to, and how to ensure operator is going to work there. He should have 100% confidence that he is not going to meet with any accident. So that has given us a huge reliability, because otherwise the operator's 50% attention will be to really see to it that he is not going to get hurt or no accidents or incidents is going to happen. So then his focus on the actual process gets reduced. That brings the slowness in operations. So the productivity is lost, the quality you sacrifice, and the operator himself has to be very confident that yes, this is the most safe and a healthy environment which is given to us. So I think these 3-4 initiatives are going to take us far ahead in the coming days now.
Right. And one of the aspects here that is also interesting is since you have now, about 30 years almost experience in the entire space related area, is there a possibility that you are looking at end-to-end design of your own engines and being able to produce all of them by yourself and scaling it towards bigger vehicles or even smaller vehicles? And the second part of this question is you now see also a couple of interesting startups coming out of India where they plan to produce their own launch vehicle as such. I mean, it's obviously logical for them to work with you to be able to produce those engines as well.
Yeah, so I mean, whenever somebody asks me about the startup, I will. Second question first is, should we really help them? Should we really share our experience with them? So I have my own, analogy towards it, or I have my own argument towards it. So even though we have more than 25 success, I mean, today's PSLV, GSLV, various satellites, the ground systems, so many different technologies. So if you really ask me, I will name that we have more than 25 success stories, which everybody should be really proud of. But should I only share with all these startups only these 25 success stories? Or should I share more than 250 the setbacks what we have got in the last 30 years? And these 250 setbacks, I cannot forget. I mean, as I cannot forget the 25 success stories, equally important for us to remember those 250 setbacks also, because those setbacks have really taught us and made these 25 success stories. Had we not learned, I don't think we could have achieved one part, one engine. But like I said, that we have made 150 Vikas flawlessly. Maybe first 1 or 2 engines, we had about 2%, 5% rejection. But the last 100 engines, we had practically zero rejection. I'm not claiming zero rejection. I'm saying practically zero rejection. Once we had some rework or maybe 1 or 2 components we have lost in that. But that happened only because we learned from those 250 mistakes what we did. Now a startup, if I really bombard him with too much of 250 mistakes, then I don't want him to get discouraged. So what we offer them is that we always share them with these 25 success stories, how it has happened. And we offer them our manufacturing facilities at very competitive or almost throwaway prices, so that they should not have one more financial burden for them to carry. And they should really think into the innovation. They should really work onto the specifications, the designs, And they should not waste their time and energy into manufacturing. Unless a startup is into new technology itself, that he wants to make a 3D printed part, then obviously it is a different story. He is going to be a manufacturing startup. But there are many startups who are coming out with new concepts. I mean, today we know that why Viking engine, the Europeans have stopped it, because the kind of fuel and oxidizer they use it is not at all a green fuel. And in fact, it has a carcinogenic impact and effects also. So now he has to think for a new fuel, which will be equivalent to give the same specific impulse, the force and time duration for that particular thing. And it has to be a green fuel. So we don't want to come in their way of thinking a different chemical reaction which will take place and still generate the same thrust. But to make that happen, if they want any manufacturing help, we will not make those 250 mistakes, and we'll try to give them the first part itself to them to get their concepts tested at ground level. So that's the way we work with the startups. We encourage startups today that they should really think independently and really not come and get biased with our views, what we have generated in this organization. Going forward, I think is going to be a little tough in the sense that now for last 30 years, we have really done a huge expertise, and we have about 150 technologies in the manufacturing area, which we have mastered it. But even though we have mastered, is our task over? I don't think, as we said, that we have started moving from one engine in 4 years or 5 years to 25 engines a year, and we are looking for 100 engines. I think we need to do quite a lot, a huge amount of work to really understand how we bring the entire mass production technology and be competitive. Finally, all that what we are talking in Indian space program, everything cannot be used only in India. We have initially 5 years, 10 years, definitely we are today falling short of transponders against our requirement of 750. What we are having is only 250. So 500 transponders are required to be built. And similarly, in every sector, not only in communication, but in remote sensing, in tele-education, in telemedicine, in whatever, disaster management, everywhere we are going to have this kind of a shortage. So scales are going to happen, but after 5 years, 10 years, 20 years, this is going to be end. So we need to also start developing the export business, export market. And if export we are going to be going to enter, we have to be really competitive and much higher reliability than what we are having today in India. We are also entering into a phase of Gaganyaan, that means a human in space. The quality requirements are going to be 3 times more stringent when somebody is going to sit inside that particular launch vehicle. So we need to learn that. So what we are doing in Godrej today is that we are really understanding as to if we have to scale by another 3 to 4 times, like we have already brought in from 4 years to 1 year and 1 year to 25 engines, and now 25 engines going to 200 engines. So that scale, how do we reach it? And by doing that, we should not increase our cost. We have to be within our cost limit so that the export is feasible, or India itself can able to afford this very effectively. So that is the first thing. The second is the huge experience in manufacturing. If we can combine with from build to print as we operate today to build to spec, conceptualization, what ISRO is doing today, what should be the mission, I think it's too far away for a manufacturing industry like us. But definitely we can contribute heavily if ISRO comes out and says that now I want, instead of 80-ton engine, what we are using it today, the Viking engine, I want another engine which is going to be 150 tons or 300 tons or 200 tons. And this is the envelope in which it has to be there. And this is the height and weight of that particular engine should be in my rocket. Then taking from there, I think we can enter from build to print to build to spec. So we have taken up that second aspect from getting into how to scale it up and reduce our cost of production, how to get into build to spec, so that we will then start doing detailed engineering. We know how to really select materials. We know how to really tolerance them. We know how to really decide on various shapes and various geometries which are good for manufacturing. We can bring in manufacturability, which most of the designers, because they don't concentrate on the manufacturing, sometimes they lose that concept and design something which is practically not possible to manufacture, and then we have to have a lot of shuffling of drawings between the fabricator and the designer, and something now what ISRO calls that as a concurrent engineering. So when they are on the design board itself, they start sharing those drawings with us and start asking our opinion as to what changes you would be happy in case you want to suggest in this design. And then they evaluate whether these designs can be changed and accepted so that the manufacturability also gets into it. So we are moving from build to print to build to spec. So that is the second aspect which we are doing. Third is, I think, how do we source the material? As I said, the raw material sourcing is done by ISRO today. And the day is not far away when we are going to be asked to source the material. The supply chain is required to be really established. So we have started Godrej Aerospace cluster, where we have some manufacturers of various materials like steel forgings, castings, and some extrusions, and somebody has a good capability to roll and manufacture those parts. Then we have some specialized processes which are used in this, but they are not required in large numbers. So we have those kind of processors who are part of our cluster. Next, what we have decided is that we will focus on to more of assembly testing, and we will farm out as many components as possible. So we have about 25 specialized machinists who have invested into 3-axis, 5-axis, 9. Support them in like what ISRO supported us. So we also support them in helping them in making their investments much easier, and give them a long-term projections, give them long-term agreements so that they can get good machines for themselves, and we promise them. And the last effort is on to really setting up huge test facilities, the qualification facilities, so that when we will design, make a build to spec of our own, we should be able to test it. We don't want to go to ISRO as far as possible, except the facilities are going to be very, very expensive, and ISRO is ready to offer those facilities at a very competitive price. But normal vibration, kinetic, acceleration, all those facilities we are investing and learning as to how to really acquire data, and from there perfect our designs. So these are the areas in which we are working.
Right. So I would love to schedule, an episode maybe in person when I'm visiting India sometime to talk about, especially the spin-offs that you talked about and the application to the larger societal applications. I think we should do possibly an episode just on that, where you talk about how Godrej has really operationalized a lot of the space technology in other sectors. I would love to do that and meet you in person at that point of time. But let's say, if, given the paucity of the time, my final question, thank you so much again for taking so much of your time in explaining all of this. So the final question I have is mostly towards young people. You think there is reasonable talent available for you to absorb today in Godrej Aerospace to put them into work, on all of these space related program, or where do you see gaps? Which kind of talent are you looking for? And what are the opportunities if people want to join you?
Yeah, so we have a very ambitious growth plan. So quite a large number of opportunities are coming up, and we have been regularly recruiting as we have been regularly investing into our infrastructure. We have created Center of Excellence in sheet metal. We have created Center of Excellence in welding. We have created Center of Excellence in machining. And these are the areas where we do our own research, our own understanding. But of course, in manufacturing to begin with, we are not into the basics. We work with academia quite well, with most of the IITs and engineering colleges in and around Mumbai. And we also work with many of the international such forums where there is a knowledge sharing, and I mean, you can really get into like we have Performance Review Institute, which is one of that is the only agency which allocates you a NADCAP accreditation. It's a very specialized certification in aerospace, which is obtained after you get AS 9100 certification, which is like ISO for all the special processes. So we are participating in that. And what we do is, I think there is a lot of focus which is required. There is one or two engineering colleges only which are making specific to aerospace. But otherwise, we have quite good mechanical engineers. We have quite good product engineers. We have some good metallurgists. We have some good chemical engineers or the chemist who can understand the various surface treatments and their coatings and their various phenomena, what happens when you want to protect the corrosion. So these are all the disciplines where we really look forward for recruitment. But I think coming with the basic degree in aeronautical engineering will really help us. And not aeronautical engineering in design, but aeronautical engineering in manufacturing. And there are no such institutions which are available. And that is where we work with the academic institutions today and trying to encourage students in their third year and fourth year to really look into the aerospace and take more of their electives and projects and their seminars into the aerospace, and we support them. I mean, our facilities are offered to them for doing any kind of a practical work or any co-guide if they want from industry, so that we can bring in our experience and our knowledge to help in making their thesis or their projects. That is where we really help and encourage. And I think all this will really build a good ecosystem. I think what is lagging today is the public-private partnership. I mean, as you know, that the HALs and BDLs and BELs and all the ordnance factories, they have beautiful and nicely developed infrastructure, but they have a challenge of their productivities and challenge of their the procurement procedures, whereas the private industry can bring it and the combination can really work. And similarly, the academia and the industry participation. And this participation should not be only to give projects to them, but to really develop products. So what we are focusing with academia is not to develop a process, but to develop a product. And in that developing the product, the academia also should take some kind of a risk share. So we are ready to give them the handsome IP rules, but at the same time, they should also be ready to take a lot of risks which are involved in any development of this aerospace parts.
Right. So thank you very much, sir, for taking so much of your time. So I think this is extremely insightful, the kind of narrative over 30 years. I'm sure that, people who are listening to the show will appreciate it quite a lot. And we would definitely want to do a follow-up episode with you just on the spin-offs, as I said.
Sure. I will be happy to do that.
Absolutely. So thanks a lot. Have a nice evening.
Thank you. Thank you for inviting me today.
Thank you for staying until the end. The NewSpace India podcast has recently started a Patreon account in order to collect your support to produce a documentary that captures the pioneering work done by many of the generation of scientists during the Sarabhai and the Satish Dhawan era. We believe that this will overcome the gap that none of the institutions in India have gone on to create a documentary-style space history project that captures both anecdotes and personal history of many of the pioneers of that generation. Please do check out the Patreon account and do consider making a contribution that will help produce this documentary. Thank you for your contributions.